Hello and welcome to our talk on a semblance of similarity, student categorization of simple algorithmic problem statements. This is work done by me, James Finney-Ansley, Paul Denny, and Andrew Luxton-Riley. Now, I know this might be a bit scary, but imagine you're an undergraduate student in a CS1 class and your professor has just asked you to solve the following question. Write a function that takes the lists of integers and returns a new list containing all the integers from the input list that are greater than 5. Some students, and we hope not many, would have no idea what this question is asking them to do. Other, more cleverer students, like Paul, might have some understanding of what the question is asking, but can't quite abstract it. Other clever students, like Andrew, will have a well-formed understanding of the type of problem they're looking at and how to solve it. In other words, these clever students have learned some kind of plan, pattern, or template for naming and solving the particular type of problem they're looking at. Ideally, we'd like everyone to be like Andrew and be able to identify the particular type of problem they're looking at, abstracting away messy and superficial details. This is where patterns come in. Patterns provide a categorization of the different types of problems that exist along with how they are solved. They provide a way of thinking and communicating about problems, abstracting the messy nature of programming and problem solving. Over the years, people have identified similar topics to patterns, such as plans and templates. But for the purposes of this study, we aren't going to make much of a distinction between these constructs. Rather, we will focus on the concepts and categorization patterns provide to computing problems. A few people over the years have said teaching programming patterns, plans, or templates, whatever you want to call them, might help people program a little bit better. It might be easy to fall into the trap of thinking that because we don't teach students patterns, they must obviously be blank slates ready to absorb anything we have to say about them. However, we believe most students coming to our courses will already have their own understanding of the different types of problems that exist in the world and how they are solved, and will continue to develop that understanding even if we don't explicitly teach them about patterns. Constructivist theory suggests it's probably a good idea to know what students know before we even think about trying to teach them. So we want to understand where students are at with their pattern-like knowledge, and hopefully, once we've figured that out, we'll be able to build upon that knowledge with more targeted instruction. There are too many different types of patterns for us to focus on in one study, so we direct our attention to students' understanding of algorithmic-like patterns. Algorithmic patterns are simple patterns often focused on processes such as finding the maximum value in a list or searching for a value in a list. We hope to look at students' pattern-like knowledge by answering the following research questions. 1. How do students categorize simple algorithmic problem statements? And 2, how do students describe the categories they identify? To answer these research questions, we got students from across their first 4 years of computer science instruction to do card sorting exercises where we asked them to put 30 questions into groups. We did 2 rounds of card sorting with each student. In the first round, we asked students to intuitively group problems. In the second, we asked students to think about the solutions to problems as they were sorting them. We did the second round of card sorting to make sure that we had one round where solution-oriented sorting was explicit. Schema theory tells us schema activation is automatic with problem representation. However, we were skeptical that merely reading problem statements without an explicit prompt to focus on solutions would be enough for this. The 2 rounds of sorting also provided 2 data points which could be compared. After each round of card sorting, we then asked students to describe the overall rationale behind each of their groups in a short, semi-structured interview. The card sorting exercises were performed on Trello. Trello was chosen after a short pilot study where participants referred Trello to other methods of card sorting. Cards were preloaded into each Trello board, and participants were asked to read through the cards and start sorting when they were ready. Participants were prompted to name each of the lists they created on Trello during the card sorting exercise. We couldn't just throw any old questions at students, so the questions were carefully written to only vary along 3 key dimensions: pattern, context, and data type. We won't go into detail as to our exact process for writing questions, but if you're interested, it is briefly described in the paper, but we'll go over a few examples of how questions could vary. Questions could vary by pattern. For example, we might give participants questions which ask them to return values in a list which are all greater than 5, or values from an input list all multiplied by 2. In this example, the corresponding patterns would be filtering and mapping. Patterns or questions could also vary by context. So we might give students a decontextualized question, just asking them to write a function which processes some data. Or we could tell some kind of story where there's a rainfall sensor recording the daily rainfall in millimeters, and we want students to process it in some way. Questions could also vary by input type. For example, we might have lists of integers as input, or we might have lists of strings as input. The main analysis in this study comes from 2 rounds of open coding of interview transcripts. During the card sort, participants named each of the groups they created, and immediately after each of the card sorts, participants described each of the groups in a semi-structured interview. These names and descriptions were coded in 2 rounds of open coding. The first round looked at what category was described by the participant. The second round of open coding looked at the language participants used to describe pattern-like categories. For example, this is a description of a group, or a name and a description of a group given by a participant. This participant called one of their groups returns a similar list, and when asked to describe it, said, "This one returns a similar list. What I mean by that is it takes the input list and then changes each element in the list." During the first round of open coding, which identified the categories described by participants, this group was identified as mapping, as the participant is describing changing each of the elements in a list. During the second round of open coding, which identified the language participants used to describe groups, this group was identified as a description of process, as the participant is describing the general process to solve each question. A more detailed description of the 2 rounds of open coding is described in the paper. The first round of open coding looked at the way students categorized problems. We found that for the first card sorting exercise, where participants were prompted to intuitively group problems, they tended to focus on surface level features such as grouping problems based on input type or the level of contextualization in the question. However, for the second sort, where participants were asked to focus on the solutions to problems, they tended to group problems based more on pattern-based features. The first round of open coding also allowed us to look at how specific students were being as they were categorizing problems. In the context of these card sorting exercises, we want students to be sorting problems at the pattern level. However, we noticed some participants were being more specific than we would want them to be, such as making a distinction between sorting lists of integers, between filtering lists of integers and filtering lists of strings. This indicated participants were able to identify what the questions were asking them to do, but were unable to abstract problems to meaningful generalized categories. One surprising result from this analysis is that students tended to identify linear searching at the subordinate level the most by making a distinction between searching for the first versus last element in a list. The second round of open coding revealed that students lacked a concise and consistent language to describe categories. Even when we identified that participants were describing a pattern-based category, participants would use a range of language to describe that category. For example, they might describe filtering as removing problems, problems that return a subset of a list, problems that keep elements if they match some condition, but very few participants would say these are the filtering problems. In conclusion, we were pleasantly surprised that students were able to kind of sort cards based on patterns when prompted to focus on solutions. We were somewhat unpleasantly surprised that students did not intuitively group problems this way, particularly considering all of these problems were relatively simple and constrained. When students did identify a pattern-based group of problems, they lacked an established language to describe the category. From this, we think students are most of the way there with their knowledge of problems, but a stronger emphasis on using established pattern languages may help solidify and clarify student knowledge. Our suggestion is to incorporate pattern languages into instruction. From their genesis, the language patterns provide has been a key focus, allowing us to communicate, think about, and name problems, providing some tangible way of navigating the messy multi-domain nature of programming. Using words such as mapping, guarded action, or linear search in classrooms, worked examples, and instructional material will help make these types of problems real. Thank you.